and staying on with this. We're finally going to get to discretization, which of course is an important topic for this workshop. This was my outline, and so last time we talked about every time you have a Hilbert complex, at every space of the complex there's a problem to be solved, which we call the Hodge-Laplacian for that complex. And of course in real applications, that problem is a boundary value problem in partial differential equations. And there's not only the Hodge-Laplacian, there's also the eigenvalue problem, the heat equation, the wave equation, various other problems. But now we're going to talk about how you discretize Hilbert complexes, because that'll tell us how to discretize Hodge-Laplacians, which means it'll tell us how to solve these PDEs. Okay, so this is think of it, if you'd never heard of this stuff before you came, you probably wouldn't have had an idea what that set of symbols meant. But now I hope you recognize the mixed form of the Hodge-Laplacian. So we have a piece of a Hilbert complex with operators D. Each has their own domain, which we call V. These are really two different operators, dk minus 1 and dk. And the Hodge-Laplacian in mixed form, we're looking for a U in the domain of D in that W, wk, and a sigma in the domain of D at the level k minus 1. So vk minus 1 and vk. And we have to, in order to get a well-posed problem, introduce the harmonic forms at level k. So we're also looking for a harmonic form P. And we have these three mixed equations. The first one telling us that U is actually also in the domain of D star, and D star U is equal to sigma. And the second equation telling us du is also in the domain of D star at the next level, and D sigma, which is dd star U, plus D star du, plus the harmonic form is equal to F. And we make U unique by orthogonality of the harmonic forms. So that's the problem we want to solve, and we want to solve numerically eventually. So we're going to use Galerkin's method, right? We're finite element people, many of us. So that means that we're going to take these spaces where the solution exists, sigma and vk minus 1 and vk, and we're going to find finite dimensional subspaces, vk minus 1h and vkh. Okay, as soon as I do that, I don't, by the way, choose a finite dimensional subspace. Well, that is finite dimensional HK. I don't choose a subspace of the harmonic forms because the harmonic forms are not something you get to choose. They come out of the original spaces in the complex. So I have to define the discrete harmonic forms. And remember what a harmonic form is. It's the orthogonal complement to B, the range of D, inside Z, the null space of D. So I define the null space of, the discrete null space is just the null space of D on the subspace, those things in the subspace that D takes to 0. And the range of D is the range of D applied to the subspace. And then this, because we had a complex, this is contained in this, and therefore I can take the no, we don't necessarily have inclusion at this point, but nonetheless I can take everything in Z, H, that's orthogonal to BH. So that's my discrete harmonic forms for an arbitrary choice of subspaces here. And then I do what you do in Galerkin's method. You write the original problem down, but you put an H on almost everywhere it makes sense. And so we're looking for a sigma H in vk minus 1 H, and a UH in vkh, and a pH in this harmonic form H that we described that satisfies equations when the test functions are restricted to those spaces. And then we have a lot of questions. The first question, this is a linear system, finite dimensional, so it's really a matrix system. Is it non-singular? But much more important question, is it non-singular and invertible in a bounded way? The bound's not too large, that's stability of the numerical method. And of course the real question we're most interested in is whether these UH and sigma H are close to U and sigma, which will involve stability and also consistency and the approximability of these given by these spaces and the consistency of these bilinear forms. We'll get to all that today. Okay?
Stupid question.
There are
Why
no
is it
stupid.
called mixed formulation?
So I believe, so mixed formulation, finite elements started in the world of elasticity, and you were looking for the displacement and the stress field in an elastic body. You typically, and let's think instead of that scalar Laplacian, so you're looking for u, the solution of Laplace u equals f, and its gradient, sigma equals the gradient of u. So in real life, in the physics that gives birth to elasticity or to the Laplace equation, you get two equations. One is the equilibrium equation, div sigma equals f, and the other is the constitutive equation that relates u to grad u to sigma. And what you usually do is you substitute one inside the other, and you get that just a formulation in u that minimizes energy. That's called the standard method. In elasticity, it's called the displacement method because the only unknown is the displacement. If you take a variational form that doesn't eliminate sigma, then it mixes together two kinds of fields. That variational form mixes together displacements and strains. That's a mixed formulation. I was going to do that, but I decided it was too complicated.
So this is mixed because it uses the two.
And let's talk about advantage and disadvantages quickly there. So it seems much simpler, just minimize some energy, just have one variable. And it's more or less always stable no matter how you choose the subspace when you minimize. When you go to the mixed formulations, it's more complicated. You have more variables. It's not a positive definite system, and there are stability issues. But remember, at the end of last time, I showed some computations where the standard method went completely bonkers, and the mixed method worked. So we're sort of forced to use the mixed method here. It has other advantages as well. And actually, nature does not always make constitutive laws invertible, so sometimes you have no choice. Okay, so the first thing is this is a non-singular system. It doesn't matter how you choose your subspaces. Just taking the obvious choice of test functions, tau equals sigma, v equals u, q equals p, you can show that if f is 0 here, then uh, sigma h, and ph are 0. So you could do the method I just said, but as we just discussed, it's a mixed formulation. It's not going to work for any choice of subspaces. For some it'll be stable and some it won't be. So that's what we're going to be getting to. And that's what I said here. Consistency and stability of the method depends vitally on the choice of subspaces. I made a remark that ZH, well, that's just defined to be the things in VH that are in the null space of Z. So ZH is contained in Z. BH is contained in B, but the harmonic forms, the orthogonal complement of one and the other, will usually not be included in that. So that means in finite element terms, this is not a subspace of the continuous version, so this is not quite a conforming numerical method. It's slightly non-conforming by the difference between this space and that space, or maybe not slightly. Sometimes that's an issue, other times both spaces are 0, it's not an issue at all. But it does make the analysis a little more complicated. Okay, so now I'm going to tell you what properties the spaces vk minus 1h and vkh have to satisfy to give you a good numerical method that is consistent, stable, and works. And the take-home message is very clear. There's basically two properties that you need, and those are the properties that make this thing structure-preserving and wonderful, and everything follows from. The two properties are numbered 1, 2, and 3, and that's because 1 should really be 0. The 1 is the obvious property that the spaces have to have good approximation properties. If your Galerkin spaces can't approximate the function, then nothing can make it work. So the first property is not one of my two properties. That is the obvious one. The spaces have to be able to approximate anything in the continuous space. And that'll be chosen because we take a mesh in piecewise polynomials and the mesh size is small or the polynomial degree is large. But now here's a structure-preserving property. We had a complex vk minus 1 is contained in vk. D of vk minus 1 is contained in vk. D takes its domain into the next domain of the next D. We need that property. So we need D of vk minus 1h to be contained in vkh. And D of vkh to be contained in vk plus 1h. So this thing is itself a complex, and it's actually a subcomplex of the original complex. Okay? We're studying complexes. That's the main Hilbert complexes. That's the main structure. We want to preserve that structure. And this is the biggie. The second property is the bounded cochain projection property. And this is something that maybe doesn't come up enough in structure preserving discretization. So usually when you say, what is this structure preserving discretization? Say, well, we have some structure, Hamiltonian system or whatever on our original problem, and we want our discrete problem to have that structure too. But we also want the discrete structure, the discrete Hamiltonian system or whatever it is, to be close to the original Hamiltonian system. We want a relationship between those. That's also very important. And in finite element exterior calculus, that's captured in this bounded cochain projection. So what does it mean? Here's our original complex. I've written the domains here and the Ds. Here's the subcomplex with its Ds, which are just the restrictions of the original Ds. I'm going to assume that there exists a projection operator from the original subspace down the original space down to the subspace. There always exists a projection, but I'm going to assume that these projections can be chosen in such a way to commute with the exterior derivative, that the projection of D of V is the same as D of the projection of V. That's a cochain projection because it's a cochain map as well as being a projection. And I'm going to assume that's bounded. And what does bounded mean? Well, it could mean one of two things. It could be in the V norm or it could be in the W norm. Because of the commutativity, if it holds in the W norm, it automatically holds in the V norm, but not the other way around. I'll assume the weaker of the two, that it holds in the V norm. That's enough for right now. And of course, the norm of this bound, that constant C, the norm of the projection operator, that's going to be an important constant in the error estimate. So I want it bounded, and like everything in numerical analysis, in a quantitative way, I don't want that bound to be too huge. Okay, and I just remind you that whenever you have a projection operator that's bounded, whether it commutes with anything or not, it gives you quasi-optimal approximation. It's as good as the best approximation. So this pi h can be used in all the error estimates. It's the same as best approximation. Okay? Okay, so now we have a structure-preserving discretization. We have a finite-dimensional subcomplex with bounded cochain projections. What do you get from this? Well, one after another beautiful property rolls right out, and they're sort of easy to prove with this. So the first thing is that this is a Hilbert complex. Well, just because we had a subcomplex of a Hilbert complex. Of course, I have to tell you what the base spaces are. The W spaces are just taken to be the same as the V spaces, but with the W norm. Finite dimensional spaces, all the norms are complete and so forth. When you have a Hilbert complex, the first thing you have is the adjoint complex. In the continuous level, we had our D stars going back here with their domains. On the finite dimensional level, we have D star H's, which are the adjoints of the discrete D's. They are not the restrictions of the D stars. They're what comes by the definition of the adjoint. But we have a discrete D star H. And what's more, whenever you have a Hilbert complex, you have a Hodge decomposition that the space is, which is WKH or VKH, is broken into the domain of the range of D plus the remaining range of D star plus the harmonic forms. So now we have VKH is equal to BKH, the range of D on the subspace, orthogonal complement the discrete harmonic forms, orthogonal complement the range of this DH operator. So we get a discrete Hodge decomposition for free, and that's an example of why it was good to create a theory like finite element exterior calculus. For 20 years, people had been discovering little discrete Hodge decompositions of different sorts in different places in the literature and making comments about them. Well, they're all special cases of this construction, basically. And the other big thing that we get whenever we have a Hilbert complex is a Poincare inequality. And so the discrete complex is a Hilbert complex, so it has a discrete Poincare inequality, which I've written here, with its own discrete Poincare constant. And of course, again, we're going to care about the size of that constant. Okay, what else do you get from the fact that we have a Hilbert complex at the discrete level? Well, what else did we take from complexes? Complexes have cohomology, finite dimensional groups, which are the null space of D mod out the range of D, which is the dimension of the harmonic forms. So I'm going to put up a theorem in a second that says you preserve the cohomology. And of course, if you're a topologist, you're very happy because preserving cohomology is one of the things you like to prove theorems about. If you're a numerical analysis, why do you care whether you preserve cohomology or not? So I'm trying to convince you that you should care a great deal. What does the cohomology do for us? We had said that the Hodge-Laplacian equation that we want to solve only has a solution if f is orthogonal to the harmonic forms. That's one condition for each dimension of cohomology. Those conditions, compatibility conditions on the data, must be satisfied to have a solution. In addition, the solution is non-unique. It's only determined up to harmonic forms, which means you add side conditions, orthogonality to the harmonic forms, to make the solution unique. You don't add them, you don't get a unique solution. You add too many conditions, you don't get any solution. Okay, suppose the homology is not preserved. Suppose there are more discrete harmonic forms than there are true harmonic forms. Then you have more side conditions that have to be satisfied to have a solution. Your real data won't have a solution because it can't meet all those conditions. If you have too few conditions, then your discrete problem will be singular. You'll have multiple solutions and so forth. So you have to preserve cohomology. What's more, you not only have to preserve the dimension, but the compatibility conditions that F satisfies is it has to be orthogonal to the harmonic forms. Then on the discrete level, it has to be orthogonal to discrete harmonic forms. Those two spaces must be close to each other in some sense, or else you're putting on the wrong conditions. They won't work. So preserving cohomology is important, so we're very happy to have this theorem. Suppose you have a closed Hilbert complex and any choice of finite dimensional subspaces that satisfy the subcomplex property and admit a bounded cochain projection pi h, those two key properties. Then we need a very, very weak approximation property that's essentially always satisfied. It says if you take a harmonic form, its best approximation, its projection, is closer to it than 0 would be. This will certainly happen in some sort of limit h goes to 0, so you can ignore this. In these cases, when you have a subcomplex with a bounded cochain projection, the projection itself, well, that's a chain map, so it induces a map on homology, and that map is an isomorphism. So automatically, the discrete harmonic forms have the right dimension, the same dimension as the true harmonic forms. What are these harmonic forms, just so you have this in mind? Well, the true harmonic form, remember, if we had, say, an annulus, was some field that swirled around the annulus that was captured the existence of that whole. The discrete one is going to be some sort of piecewise polynomial, so not the same. But then we have a formula that says their two are not too far apart. So it must be some discrete approximation of the true harmonic form. This too far apart uses the notion of the gap between two spaces in a Hilbert space. Basically, the angle between the finite dimensional spaces is small. And what do I mean by small? Well, it's good as the best approximation, or the bounded projection of Q in the subspace. So it's as good as the subspace approximation allows. So this is a great theorem. This tells us that the true problem, that the discrete problem that we're solving, which is here, really has the right number of it matches that problem. It has the right number of side conditions, which is what the P is taking care of, or the compatibility conditions, the right number of side conditions, which is what the Q is taking care of, and the conditions are not too far from each other. So we have a chance of proving convergence. Okay, then now, how do you prove convergence of a Galerkin method? Well, how do you prove convergence of any method for differential equations, numerical method? You use the fundamental theorem of numerical analysis, which says that discretization method converges to a true method if it's 1, stable, and 2, consistent. The consistency error goes to 0, and the stability constant stays bounded. So How are we going to get stability? Well, stability is well-posedness of the discrete problem and its dependence on H. How do we get well-posedness of the discrete problem? Well, the discrete problem is the Hodge-Laplacian for a Hilbert complex, the discrete Hilbert complex. And how do we get well-posedness of a Hodge-Laplacian for a Hilbert complex? Well, we gave the proof, or we talked a little bit about it. It only depends on the Poincare constant. That's what the well-posedness constant is for the abstract Hodge-Laplacian. So if the Poincare constant doesn't blow up, the method is stable. And that's the next theorem. Suppose you have a Hilbert complex and you take some finite dimensional subspaces that satisfy the subcomplex property and emit a bounded cochain projection. Then here's the Poincare condition, and with an explicit constant. It's the same Poincare constant it holds at the continuous level times the bound on the bounded cochain projections. So so these first two terms multiplied together is a discrete Poincare constant, or a bound for it. So Cp, of course, doesn't depend on H, so as long as the pi H operators are uniformly bounded, we have a Poincare constant that's uniformly bounded. Once you know that, well, now you can use the theory of Galerkin methods. We have stability, and that's going to lead us, if we didn't have a slight inconsistency due to the fact that the harmonic forms, discrete harmonic forms, are not contained in the true harmonic forms, it would just be the first three terms. The approximation would be as good as the best approximation, quasi-optimal. There's an extra term that comes from the difference of harmonic forms, but because of the gap between the true harmonic forms and discrete harmonic forms, we had a bound for it. You get a term here, and this term is basically the size of the square of the previous term, so it's very small, so let's not worry about it. So this is it. This is the equivalent of the theorem for the scalar Laplacian u minus UH, and the one norm is less than a constant times the best approximation. We have that for every abstract Hodge-Laplace problem, as long as we use a discrete Hodge-Laplacian coming from finite dimensional subspaces with subcomplex property and bounded cochain projections. So this is the theorem. Out of this you get powers of H if you're using piecewise polynomials and so forth. There's the main convergence result.
Christian, where are the boundary conditions at the moment?
Boundary conditions are in one of two places. If you're using if you don't put any boundary conditions in your spaces VK, they're all coming out naturally. So that would be the case like solving a Neumann problem. Or alternatively, you build them into spaces VK and use spaces like H01 and H02, and then they're in there essentially. But this is all abstract, so I don't have to have no special equations for that. Okay, so Blanca.
You are saying that the last term is for the square of the approximation. How can we see that? I mean,
the way you see that, so this says you take a piece of U and you take its best approximation from the subspace. So that'll be order H to the R if you're using piecewise polynomials of degree R. And this says you take a harmonic form, normalized to be of size 1, and you take its best approximate, or you take its projection in the subspace. That'll also be H to the R.
but that means you need, for these projections, you also need some approximation properties.
Yes, remember that's why the two properties were labeled 1, 2, and 3. That's 1. So otherwise, I mean, this theorem is true as it stands, but saying, well, this is, I mean, even these terms, why do they go to 0? Well, that's approximation properties. The best approximation is only a good thing if the best approximation is small. Okay, so sort of we're done with the theory. Not really, but in the abstract theory, this is the hypotheses, subcomplexes, bounded cochain projection, and the conclusion, quasi-optimality, is the key result. And it works for any Hilbert complex and any choice of subspaces satisfying that. Now, you don't stop there. If you're doing finite elements for the Laplacian, you prove the H1 error estimate is order H to the R. Then the next thing you want to do is you want to prove in L2, you get a pickup, and it's H to the R plus 1. We want to do that here, and it's a little complicated. You want to consider separately sigma, d sigma, u, and du. And that's all done. That's done in the 2010 paper and bulletin of the AMS. very extensively. It takes about 10 or 12 pages, uses all the Nietzsche tricks and duality tricks known in mixed methods, and a few more maybe. This is the result, and I don't think I'll go through it. All these E's mean best approximation of something, and each of the quantities is bounded by sort of the best approximation of things and terms that pick up extra H's. Let me not go through it. So let me do a numerical example instead. So, I don't know, and my advisor used to say to me, we don't have to compute things that we can prove theorems that we work, but I actually like to because I don't believe my theorems. And then if both of them work, I start to get some confidence. So let's take a simple example and just make sure we see the rates of convergence this theorem says we should see. So now I'll get away from the abstract Hodge-Laplacian. I'll use the de Rham complex and take, in this case, the one-form actual Hodge-Laplacian with the natural boundary conditions, no boundary conditions in the spaces H1 and H rho, but by integration by parts we get u dot n and rho u equals 0 being imposed. And so that's the mixed formulation when we use one forms and the extra variable sigma is 0 forms in H1. So we have a scalar variable in H1 and a vector variable in H rho. And the finite elements we're going to use are going to be based on a subcomplex. This tells us what the subcomplex is. We take our two-dimensional domain, we triangulate it, we take continuous piecewise quadratics for the sigma h. We take not the lowest order, but the second lowest order rotated Raviart-Thoma elements, H rho, not H div, H rho Raviart-Thoma elements for UH, and piecewise constants for the image of the rote. So the rote maps the Raviart-Thomas into the discontinuous piecewise constant, piecewise linears, DG piecewise linears. This is a subcomplex. This space, the gradient of Lagrange's is contained in Raviart-Thoma 1s, and the gradient of Raviart-Thoma 1s is contained in DG linears. And you can prove that it has bounded cochain projections. So we should get the theorem with the constants all bounded. And now I've shown you the rate that we get on sigma, which is, and the rate we get on d sigma, grad sigma, and the rate we get on u, and the rate we get on du. There are no harmonic forms in this case, in this computation. And sigma we're using quadratics, so the best possible rate we could get in L2 is it's third order convergence, and we get third order on the nose convergence. Grad sigma is sigma error in H1, so with quadratics we can only get second order convergence, and we get second order convergence. U is in the Raviart-Thoma space, which contains P1 but does not contain a full P2. It's between P1 and P2, so we can't get better than second order convergence on U. And the Raviart-Thoma elements are cleverly constructed, so when you take the root of them, you still contain the whole space of piecewise linears, and so we get 2 on that also. So we're getting optimal order on every component, and that's what the theorem says always happens in all cases. And this one I'll do quickly. Pascal brought up a question related to this. This is a situation where I'm solving this same PDE, grad div curl root. Well, if you write out this PDE and do your calculus, you might remember that on the vector u is u1, u2, u1, u2 in this case. That operator just becomes Laplace u1, Laplace u2. It's the vector Laplacian. That approach doesn't lead to boundary conditions like that. That approach leads to Laplacian kind of boundary conditions like u equals 0 on the boundary. So you could try to solve this equation with u equals 0 on the boundary as your boundary conditions. It wouldn't fit into the nice Hilbert complex structure, but you could do it. You could use the mixed method. And we did it, and you can use the mixed method and you get an answer, and it's very suboptimal. Don't have the Hilbert space structure. It's not a structure preserving discretization, and it doesn't work so well. Okay. Oh, by the way, what time do I have? 30 minutes. Okay. Oh, 31. Okay. Perfect. I can almost do it in that amount of time. So the situation is we just finished the abstract theory that I'm going to go over. And now the question is, well, suppose I have a Hilbert complex in reality and I got to come up with some finite elements to use. That means I have to make a subcomplex with bounding cochain projections. How the hell do I do that? And we're going to talk about that for the Rham complex, the running example. So let's put up the Rham complex. Well, we've been looking at the Rham complex as 0, goes to L2 vector fields. L2 scalar fields goes to L2 vector fields, goes to L2 vector fields, goes to L2 scalar fields, where these are grad, div, and curl, grad, curl, and div. And the domains are H1, H curl, H div, or maybe H01, H0 curl, H0 div. And we've seen the two-dimensional one just a moment ago and so forth. So we're going to do that. We have a different Hodge Laplacian in each level. But we're going to do this. I don't want, so one thing I hate, well, sorry, there's probably lots of people in the audience who do this, so I should be careful. One thing that always troubles me is when somebody writes a paper and says section 3, section 1 is the introduction, section 2 is the notations, and section 3 is the H1 case. Section 4 is the H curl case. Section 5 is the H div case. And they're all very similar, but they all start over from the beginning. I want to do all the cases at once. And as the maxim I said in the first lecture, if you don't get it right in n dimensions, it's not going to work in 2 dimensions. So I'll just do it in n dimensions and get it so it gives you all these cases in any number of dimensions in one fell swoop. So that means we have to define differential forms. The strength of differential forms is that the exterior derivative operator, a basic operator in differential forms, is in different cases, different degree differential forms, the grad, the curl, and the div. So you define them and you get their properties all at the same time. And similarly, other properties of differential forms are doing many calculus identities at once, basically. So now the slides are terrible. They're very busy at this time. So I'll do some stuff on the board and do some of the slides. Let's see what we need. So a differential form does not have a difficult definition. We have an n-dimensional domain, and as we know, it's a function from the domain to the alternating k-linear forms on Rn. And that moves immediately to a manifold. If omega was a manifold, not necessarily contained in any Rn, just a abstract manifold, it would be a function from the manifold that at each point ended up as an alternating k-linear form on its tangent space. It's a section of the alternating k-bundle of a manifold. These are fancy words. Okay, so then what does that actually mean? Let's go back to the Rn case. What does that mean? Well, a zero form, k is nothing, so it's just a function. So zero forms are functions. A one form, k takes a point to a linear functional on Rn. In other words, it's a function from omega to the dual space of Rn, and most people think of the dual space of Rn as Rn, so it's a vector field under that identification. Before I go on to the next case, let's just write some notation down. The usual, how do you identify the dual space of Rn with Rn? Well, you use the inner product or the standard basis, either one will go. We want to give a basis that will correspond to the standard basis of Rn, and the basis elements can be called dxi, I equals 1 to n, where dxi is by definition the thing that takes a vector in Rn and gives its ith component. So it takes the standard unit vector and gives 1, and the other unit vectors give 0. Okay, so that's the name that's used in this business for the standard dual basis to the standard basis in Rn, called dxi. That means a one form is u is just a function at any point x, let me put the x down here, it's some value that depends on x times dx1 plus some value that depends on x times dx2 and some value that depends on x times dx3. So that's a general, this is a general element of the dual space of R3, and the element depends on x, so it's a function into the dual space of R3. So of course we can identify this with f1 of x, f2 of x, f3 of x, and that's why we say a one form is really just a vector field. In what sense is a two form also just a vector field? Well, the standard basis for, if we take, say, all 2 of Rn, the basis can be written using wedge product as things like dxi wedge dxj, where the meaning of this, well, this would take, so we want an alternating form that you're given 2 vectors. Well, you could take the standard vectors in Rn, but since it's alternating, you should take them in increasing order. So you could take E1, E2, E1, E3, E2, E3, etc. And this is the one that takes EI, EJ to 1 and the other ones to 0. This is, of course, the negative of dxj wedge dxi. This is the bilinear form you get by tensor producting these and then taking the skew symmetric part. And so in 3D, if U is a 2 form, then U at a point x is equal to some f1 of x times dx2 dx3 plus, maybe call it g, plus some g2 of x times dx1 dx3, and it's conventional to put a minus here, it gets nicer formulas, and g3 of x dx1 dx2. And so we can identify this with g1, g2, g3 of x. If we were in n dimensions, it wouldn't be 2 forms that were vector fields, it would be n minus 1 forms that were the vector fields, because the component is the one I left out here. Okay, and so here's the general case. If you have a k form on Rn, a basis for the alternating k forms are dx sigma 1 wedge through dx sigma k with increasing sigmas, and a linear combination of those is a general differential form with spatially dependent coefficients. Okay, so with that definition we've gotten differential forms, and then there's a lot of operations on them that are all sort of elementary. A wedge product, which is sort of a tensor product that's been skew symmetrized. The exterior derivative, which I probably should put down in terms of components. If you have f of x times one of these things like dx2 wedge dx3, or dx sigma 1 wedge dx sigma 2. I'll do it for a 2 form, but this is a general thing. D of that, you would just take the partial derivatives of f times dxj and wedge that with the rest of this stuff. And the sum of that is j goes from 1 to n. That's the exterior derivative. And that captures in 3D the grad, the div, and the curl. In ND, the first one is always the grad, the last one is always the div. The ones in the middle are different things that don't have simple names, well-known names. A k-form can be integrated over a k-dimensional subset. We already saw that. It was this picture here. There's a pullback operation if you have a mapping from one domain to another. You can take a differential form here and pull it back in a natural way there. And that's what gives rise to things like the Piola transform. It's the same pullback that Charlie was talking about for 0 forms. For HDiv n-1 forms, it's the Piola transform. For 1 forms in 3 dimensions, it's the so-called covariant transform and so forth. So a lot of calculus operations come that way. You might remember, many of you have probably done this calculation, that if you do this and you take a vector field u here and a scalar field p here, and you pull them back to a vector field u here and a scalar field p here, and you take the inner product div u p on omega hat, and you take the inner product div u p on omega here, this is the Piola transform to pull back for u, but the regular composition for p, these are equal. That's a pain in the butt computation. The first 3 times you do it, you always get it wrong, and you have to keep trying and so forth. That's a very standard fact about pullbacks. And we get one of these facts at every level k in every dimension. Comes straight out of this. If one space is contained in another, like for example, boundary omega is contained in omega, you can pull back the inclusion map. That's how you define the trace of a differential form. The trace of a function is the usual thing, just restrict the function to the subspace. Restrict it from omega to omega hat. The trace of a one form is the tangential component. So you had a function that was acting on any one vector. Now it only acts on the subspace on vectors tangent to that. So that gives you the operation u goes to ut. The trace on an n-1 form takes the normal component of the vector field. So these different calculus operations all get one name. They all become the trace. And Stokes' theorem relates the exterior derivative in the trace, and you get, this is many different theorems. Even in 3D, it's Stokes' theorem and divergence theorem and the fundamental theorem of calculus. And in ND, it gives you many more things. Okay, so those are the major things about differential forms. That was differential forms 101. And get used to it. If you haven't worked with it before, you'll sort of get used to it as you work with it. Okay, now get back to finite element exterior calculus. We take the point of view that that the exterior derivative can be viewed as an operator on L2 whose domain is h lambda k, which means the thing's in L2 such that du is also in L2. And there's a theorem that's not easy to prove, that if omega has a Lipschitz boundary, this operator always has a closed range. So then the de Rham complex, the L2 version of the de Rham complex, which is the one that we like to use, is this Hilbert complex with unbounded operators, makes sense in ND, and is equivalent to this 3D version through these identifications, and extends it to ND. And our goal is, given this complex, the de Rham complex in n dimensions, to find finite dimensional subspaces of these L2 spaces, which are in the domain of the Ds, and have good approximation properties, and form a subcomplex with bounded cochain projections. So for example, for zero forms, we want to find a subspace of H1, which has good approximation properties and that we can use in the subcomplexes. So of course, we're finite element people. How do we approximate H1? We triangulate the domain into simplices, and on each simplex, we take the space of all polynomials of degree r or less, and we define degrees of freedom that let us patch them together so that they're continuous from one to the other. Those are called the Lagrange elements. What I want to do is I want to generalize the Lagrange elements from zero forms. I want to get also the right things for one forms and two forms and three forms. And that's of course known to be hard because, say, for n-1 forms in 2D, that leads to the Rabiart-Tolma elements, which were not obvious at all. Okay, how do finite elements work? Well, going back to CRLA, you take your triangulation, which for us will be simplices. For each triangle in the triangulation, you take a space of functions, which will typically be polynomials. These might be vector-valued functions or something else, depending what you're trying to do. And most important, for each triangle, you have a set of degrees of freedom, which means a set of functionals on the shape functions. And here's something that CRLA forgot to emphasize, but it's crucially important. So each one is associated, he did it implicitly, each one is associated to a face of the simplex. And these are unisolvent. In other words, they form a basis for the dual space of the shape functions. So the number of them is exactly the dimension of Vt, and they can be assigned arbitrarily to determine a unique element of Vt. And then that tells you how to define the finite element space Vh. It's those functions which are piecewise in Vt. And when two t's have a common face, the degrees of freedom associated with those faces take the same values, single value degrees of freedom. And that's the general definition of a finite element space. One thing you get out of there is the inter-element continuity is not specified a priori. It's specified by the single valuedness of the degrees of freedom. And a consequence of all this is that given any function in your original domain, you can project it into the finite element space using the degrees of freedom. So let's remember how the Lagrange finite element space works. In finite element exterior calculus, it has a crazy name. It's the polynomial of degree r zero forms. Well, we know a zero form is a function, so they're rth degree polynomial functions on a triangulation. And that's a space for h lambda super 0, which is another name for the Sobolev space H1. So for each t in the triangulation, that's a simplex, we have a space of shape functions, which is nothing other than the polynomials of degree r on the triangle, which in finite element exterior calculus language would be PR0 forms of the triangle. R has to be greater than or equal to 1. And the degrees of freedom are this famous picture of how the degrees of freedom lay out for Lagrange elements. There's one at each vertex. So for each this means the zero-dimensional faces of the simplex. Those are the vertices. For each vertex, we have the evaluation at the vertex as a degree of freedom. There are r minus 1 on each edge. For each edge of the triangulation, we have, and you can take the moments of the restriction of u to the edge weighted against polynomials of degree r minus 2 to get your r minus 1 degrees of freedom. And for each face, you do a similar thing. You take the restriction to the face, and you take the integrals against polynomials of degree r minus 3 in the face. You drop down in degree, and you get that set of moments. And then you would go in the interior and take polynomials of degree r minus 4 for the weights and so forth. So that can be written in exterior calculus language by this formula for each dimension d greater than 0 on a face of dimension d, f. You take the restriction of the trace of u on f as a 0 form, which is just a restriction. You weight it by q, which is a polynomial of degree r minus d minus 1. It goes down as the dimension goes up. And I claim that this is not a 0 form. The weighting function q, it's actually a d form on the d-dimensional face. A d form is also a scalar because there's only one d form in d dimensions. Would be something of the form f of x, and then the only thing you can put here is dx1, which dx2 up to dxd. That's the only increasing sequence from 1 to d. So, and why do I say this should be a d form rather than a 0 form, that function? Well, when you multiply these together, this is a 0 form, this is a d form, the whole thing's a d form. D forms are what we integrate over f. So in differential forms, if u is a 0 form, you shouldn't write the integral over omega of u. 0 form should be evaluated at points. You should write the integral over 0 forms of u dx, which means dx1 through dxn. That's integrable. Turn the 0 form into a d form by putting in dx, and then you can integrate it. Okay, and then there's a theorem that you prove in every finite element course, that the number of degrees of freedom that I just listed down here is exactly the same as the dimension of the polynomials of degree r. So that's a beautiful theorem. This arrangement of dots on a simplex is exactly the dimension of the polynomial space PR. And if all the degrees of freedom vanish, then the function vanishes, so we have unisolvents. And you prove that single valuedness of these degrees of freedom is equivalent to assuming that, insisting that the function be continuous, which is equivalent to assuming the function be in H1. Okay, that's Lagrange elements in a word. And that's the proof of unisolvents and the proof that the numbers add up, and I'm going to skip that. Okay, so now what do we want to do? We want to do what we just did, but not for zero forms, for K forms. So we introduce the space, okay, and let me foreshadow where we're going to go. We're going to find out if you're dealing with K forms and you want a polynomial degree R, you fix some degree R that you want to deal with as your polynomial degree there, and you fix your triangulation, there are two finite element spaces that are very natural that come out. So for every K and every R and every triangulation, there are two beautiful finite element spaces for K forms with the names PR lambda K of the triangulation and PR minus lambda K of the triangulation. For every K, 0 to N, every R greater than or equal to 1, every triangulation by simplicities TH, these two spaces are the finite element spaces we want to use. And now you might say, well, so you told us about one of them for zero forms, what's the other one for zero forms? And they're equal to each other exactly if K is equal to 0. And in all other cases they're unequal. Although in the case K equals N, scalars again, they're not equal to each other, but PR minus is PR minus 1. So for zero forms and N forms, ordinary functions, there's only one space. But for all the other ones, vector fields and the other things that happen in higher dimension, there are two spaces. So we want to define them today. It's easy to define PR lambda K, or relatively easy. At least the shape functions are easy. They are the PR lambda K in a triangle, which just means that when you write out a K form, the coefficients should be polynomials of degree R. So I guess this is just a notation slide. This notation, PR lambda K of omega, means the differential K forms whose coefficients are polynomials of degree R or less. And the homogeneous polynomials I write HR lambda K. It's easy to get the dimensions of these. The number of coefficients is n choose K. That's the dimension of alt K in Rn. And each coefficient is a polynomial of degree R, which means its dimension is R plus n choose R. The homogeneous polynomials, the formula is this. The polynomials themselves form a nice de Rham complex. The derivative of a polynomial of degree R function is a polynomial of degree R minus 1 form. That's just as the gradient of a polynomial of degree R is a polynomial of degree R minus 1 vector field. And you saw the definition of the exterior derivative. It has one partial derivative in it, so it lowers polynomial degree by 1 each time. Same thing with the homogeneous polynomials. These complexes are no good for numerical analysis until you introduce a mesh. There's no cohomology in these things. These are, so we can't just use one global polynomial. We have to now apply this element by element, but we can use these for the shape functions.
If I concatenate two V's, why is that 0 in this case?
So that's a good question. So why, if I take this definition and I apply it twice, I get 2 zeros? And the answer is because partial second derivatives commute with each other. You end up getting terms like EF dx1, and then you differentiate it with respect to, then second time you'll get d2f dx1 dx2, dx1 wedge dx2, and you'll also get one that'll be d2f dx2 dx1 dx2 in the opposite order, and also these will be in the opposite order, and these are equal to each other, and these are negatives of each other, so they'll cancel. So it's a very simple calculation. Any other questions? Okay, well, there's one more tool to introduce, just when you were thinking, oh, one more I got to get through. It's really important, it's really simple, but it has a scary name. I don't know how to pronounce it, Koszul. It comes from topology. I'm very proud of the fact that I think I'm the first person to bring that word into a numerical analysis paper. So the exterior derivative D is a way to define one operator that gives you grad, div, curl, and other stuff. The Koszul operator kappa is a much simpler operation, no derivatives. It's take a scalar field, scalar function, and multiply it by x, x being x1, x2, x3. Or take a vector field and dot it with x, or cross it with x. Those operations are the Koszul differential, and there's n of those in n dimensions. And it can be defined in the following way. Think of this vector field. What vector field is that? Well, at 0, 0, it's 0, 0. At 1, 0, it's 1, 0. At 0, 1, it's 0, 1. This is the identity vector field. At any point x, it's x viewed as a vector. Now, take a k form that takes k vectors and spits out a number. For the first vector, plug in this guy x. Then you have a k-1 form. It has k-1 slots left. That's the Koszul of the original k form. So that's this statement. Take kappa from the k form to k-1 form is contract with, which means stick in the first position, the identity vector field. Now, if you think that if you have a polynomial of degree r k form, you stuck an x into it, so now you have an extra x in there. So now it's a polynomial of degree r plus 1. It was a k form, now it's a k-1 form. So it does the opposite of the exterior derivative, which decreases polynomial degree and raises the differential form degree. This lowers the differential form degree k, but raises the polynomial degree. So you get a map from PR lambda n to PR plus 1, lambda n minus 1, to PR plus 2, lambda n minus 2, and so forth. And this is a complex. Who can tell me why it's a complex?
K squared is 0.
Why is k squared 0?
Similar argument to that one.
What?
Similar argument to that one. Just swap.
Easier.
Contracting the same vector twice.
You contract the same vector twice, so you stick x in the first slot, you stick x in the second slot, you had an alternating form, it must be 0. Okay, what is it explicitly? Well, if you apply k to a 0 form, it's 0 because you'd have a -1 form, and the -1 forms are all 0. If you apply k to a 1 form, well, a basic 1 form is dxi. You just get xi. You evaluate x, and you take its ith coordinate. So k of dxi is the ith coordinate function. So k sort of erases d. That's what it does. You have a Leibniz rule for contraction, so you get something like that. So here's the general formula for kappa. It could have just started here if we wanted. Kappa of a function times dx sigma 1 wedged through dx sigma k. You erase one of the d terms, dx sigma I, but leave x sigma I there. So you erase one of the d's, and you do that for each of them in turn and take the alternating sum. And the f just goes along for the ride. So it's sort of weird. Now you write it down in 3 dimensions, and to go from a 3 form, which is a scalar, to a 2 form, which is a vector, you're multiplying by x. To go from a 2 form, which is a vector, to a 1 form, which is also a vector, you're crossing with x. And of course, if you multiply by x and then cross with x, you get 0. And you go from a 1 form, which is a vector, to a 0 form, which is a scalar, you're dotting with x. Oh, 2 minutes. Okay, well, in that case, I'm not going to finish. So I'll do a little more of this next time. There's one theorem, just one, beautiful lemma about the Koszul differential. If I start on a space PR lambda k, if I do d, I increase the form degree and decrease the polynomial degree. I could do kappa and go back. Or I could do kappa first and then do d and go back. And I can add them. And the amazing formula, called the homotopy formula, is d kappa plus capital D applied to a differential k form, is the same k form back again times its polynomial degree. and this is only true if it's a polynomial with homogeneous of that degree, times its polynomial degree plus its differential form degree, r plus k omega. And that's the proof, so it's not terribly difficult. We won't go through it. Everything important about kappa comes out of this formula, so this is the one thing to learn. Okay, so that was our last tool, and I don't have time to use it, but so where are we going here? We're trying to find the spaces to use as finite elements for k-forms. We have a good set of shape functions, PR lambda k, the polynomials of degree r. Using kappa, we're going to find the PR minus lambda k forms. For each one, we have to define a set of degrees of freedom. We'll also do that using these spaces, and those spaces will give us our complexes of bounded cochain projections. And in one fell swoop, we will have dealt with Lagrange elements, DG elements, Ravier-Thoma elements, Nedelik elements of the first and second kind, Bretzi-Douglas-Marini elements, and all their generalizations to higher dimensions. Okay, thank you.
Do we have questions before we leave for lunch? Yes.
Quick one. Is this homotopy formula proved using Cartan's formula
It
for
is.
the derivative?
That's not the proof that I wrote up there. That's a very beautiful proof. In our actor numerical paper, that proof is done in a footnote, I think. It's a very short and nice proof, but you have to know Cartan's magic formula.
Do you have an example where you use a Hilbert complex which doesn't terminate, so where you don't have 0 at the end, like at the beginning?
I
Because
don't.
Your theory, I mean, just makes use of a little subchain of this. So
Correct.
It should be fine.
Yeah, I don't know if I don't have an example, but you're perfectly right that all you need is, yeah,
Go through, right?
that's correct. I just don't know whether we have such a thing. Andres?
So you have your complexes with the exterior derivative. Do you also have complexes with covariant exterior derivative?
Covariant exterior derivative.
Where you replace the partial derivative by the covariant derivative?
So if you're on a manifold, you would need, well, the exterior derivative could be written in terms of the covariant derivative.
You need a flat connection to the.
But let me see.
It's not a complex because d of d is curvature.
Well,
not zero.
if it's flat, you have d squared. It's 0. But so.
So let me say something that Hans will appreciate, and maybe Andrea will like this, which is, so we did this on Rn, where we have extra structure. So what do we need? To define the differential forms in the de Rham complex, we don't need any structure beyond that of a manifold. Every manifold has a de Rham complex on it, has all the d operators. Your question doesn't apply because there is no covariant derivative yet. To define d star, to define the Hodge Laplacian, to find harmonic forms, to find Hodge decomposition, I need a metric on the manifold. I could probably get away with a connection, but I need a little bit more. I need a metric. And then we can ask your question, and then I think d relates to the covariant derivatives with that metric.
Are there any physical systems which have a Hamiltonian where you cannot apply your exterior calculus to? Like, are there any PDEs we would like to solve which you could not solve yet?
No, I can do everything. No, there's so one of the tough questions was, what PDEs does this apply to? How broadly applicable is this theory? And it's bit by bit fight and learn about another one and get another one. We're getting more and more and more interesting complexes, but it's certainly not true that every PDE that arises fits naturally in a Hilbert context framework, right? This is an important class of problems, but it's not all problems.
If there's a Hamiltonian underneath, is that something which is enough?
We have the right people in this room to maybe figure that out in the next couple of months. I would love to know the answer to that. Maybe Hans knows. Do you know the answer to that question? Okay.
Could you start with a non-conforming space actually, and like Koszul or something like that?
You define non-conforming approximations. I believe so. But actually, I'll say this because we've got a lot of finite element experts here. in my opinion, even for standard finite elements, H1 finite elements, the theory of non-conforming elements is nowhere near as systematic and fully elaborated as, I don't even know what the most canonical.
This is suggesting that they should not be used or what?
No, great problem to work on. But so it would be hard to come up with a completely systematic theory of non-conforming finite elements for this, because I don't even know how to do it for zero forms. But it's a good question, and there probably are some things done. I don't know if anybody can think of some right off. Any other questions? Pascal?
Yeah, instead of solving odd Laplacian or variants of it, could you imagine applying your setting to the uncoupled problem? That is, first equation should be d something equal, and then the other d star d something equal something. So instead of solving d star plus d star d equal, put it as a system of two independent equations. So with first exterior derivative and then the star, the odd.
Let me see, is this the one that we get?
No, the first equation should be du equals something, and the other d star equals something.
Well, at least in some cases, so let's look at...
First order system. Two first order equations.
With the formulation.
So in 2D, for example, you could look at a problem like this, and of course that means f is determined up to constant. F has to be a gradient, so little f is gradient of big F. So this problem that I wrote down obviously only has solutions for special f. They have to be gradients, right? So f is a gradient of capital F. If I know capital F, I can put capital F here and erase that. And so that's a way to approach a problem like this. We could try to do this a little more systematically. Is this of this form that you're talking about?
So that is, instead of starting with the whole Laplacian, start only with the exterior derivative given and then the dual given.
So you want me to write it as du equals...
Yes.
I think we'll leave this
Exactly.
for offline discussion.
Fair enough.
Excuse me?
You and I will talk after during the lunch period.
Discussion.
Thank you so much. And